Welcome to this video in which we're going to talk about the relationship between equilibrium, and when you see equilibrium you should really start thinking about K, Kc, Kp, Ksp, whatever the K is, and free energy, delta G. By the time we're done with this video we'll have an equation that relates the two of them. But before we do that, I need to talk just a little bit about the relationship between K and what's called Q, so the idea of reaction extent. And so K is when a reaction is at equilibrium. And so in a problem you'd see something specific like when the reaction has reached equilibrium or an equilibrium mixture contains, words like that. But if you just have some other random composition, right? So any random composition of amounts, we would call it what's called Q. So again, I'm going to think about my favorite chemical reaction. A plus B makes C plus D. And we already know that if I wanted to calculate a K, I would calculate it with C to the C, D to the D. So products to their exponent coefficients over reactants to their exponent coefficients. And I would be ignoring phases like solid or pure liquid because they don't belong here. Now this is only for what we call an equilibrium mixture. For anything else, we can calculate an idea that's called Q. And by the way, it's a little confusing because it's calculated the exact same way. So I have to figure out from the context of the problem that this is not an equilibrium mixture, and we'll talk more about that later. So this is for any combination of concentrations, right? And so the problem would specifically say that. And K and Q are related in three ways. The first one is if you know K and Q and you find out that Q is less than K, that means that the reaction is proceeding left to right. What am I doing? I'm losing reactants and gaining products, right? So I'm making products. In another possibility, if Q is greater than K, what do you think? It's doing the other thing. Reaction is going right to left. What am I doing? I'm making reactants and losing products. Or, in the case that I find out that Q and K are exactly the same thing, then we're at equilibrium. Right? Number one, I'm making products faster than I'm making reactants. Number two, I'm making reactants faster than I'm making products. Number three, the speed at which I'm going reactants to products is the same as the speed I'm going back from products to reactants, or I'm at equilibrium. So here's an example. So I have a reaction. I'm taking H2 and I'm reacting with I2 to make HI, and the problem very helpfully gave me a K. It also gave me a bunch of numbers. It gave me some moles of H2I2 and HI, sorry, that is the wrong chemical there. And it gave me a certain vessel size. And the question to begin with is the mixture currently at equilibrium? If they're asking me that question, I know that my goal is to calculate a Q, right? And I would know that that would be from HI squared over H2 times I2. Now, since I need concentrations, I'm going to quickly do that, right? I know that this concentration of HI would be these moles over the 2 liters. And I know that the concentrations of H2 and I2 would be those moles over the 2 liters. So when we convert that, we get this, right? I get a concentration of 0.05 molar for the HI and concentration of 0.25 molar for both the H2 and the I2 since they started at the same moles. And if I do that math, I find that Q is equal to 0.04. Again, Q, just like K, is unitless. And I look at that K up there at 49.7, and I notice that Q is less than K. What does that mean? That means that my ratio of products, HI to H2 and I2, isn't big enough yet, right? It's too small. So what is my reaction doing? Reaction is proceeding spontaneously, right? I don't really have to say that because that's implied, but I can. Which way is it going? Well, I haven't made enough product yet, so it's going from left to right, Right? That's how I diagnose that. I use Q and I compare it to K. And if this sounds just a little familiar in our last video on introducing the equilibrium constant, that's because it should. So let's look at our three cases again. Remember, Q is less than K, and we said reaction is going from left to right, right? I'm still making products. Or Q is greater than K, the reaction is going right to left, right? I'm losing product and making reactant. Or Q equal to K at equilibrium. Well, those relate directly to delta G, because remember, when we calculated a delta G that was negative, we said that we were spontaneously making products. Or when we calculated a G that was positive, we called it non-spontaneous. What that really means is that the reaction is spontaneously going backwards. I have too many products and not enough reactants. And when Q equals K, delta G equals 0, and I'm at equilibrium. So there's this mathematical relationship that apparently I can tie G to Q, right? And the mathematical relationship turns out to be this. Delta G equals minus RT ln K. Let's take a moment and talk about some units here. Just like before, right? K is always unitless. Delta G, if you remember from our previous work with it, is in joules or kilojoules, but you need it in joules for this equation. Temperature should be in Kelvin, and R, there are two versions of R. Remember, there's the 0.0821 liter atmosphere per mole Kelvin that you use in PV equals nRT, the ideal gas law. That is not the one you want here. It should be 8.31 joules per mole Kelvin. So that's why your temperature better be in Kelvin, and your G better be in joules. So this particular relationship, delta G equals minus RT ln K, is one that you want to be prepared to work with. And so let's try an example. So here's an example. We've got silver chloride solid dissolving to make silver ions and Cl minus ions, and we have a delta G that's 55.6 kilojoules. We could figure out from this whether it's reactant favored or product favored. I have a guess. I notice that this is a positive number. And remember, delta G is minus RT ln K, so I'm going to expect that the K is going to be pretty small when this comes down to it, because this is something that we would call non-spontaneous, and non-spontaneous things don't go very far. But let's do the calculations to try and understand that. So let's look at my delta G equals minus RT ln K. And like I was mentioning before, it's very important to make sure that you convert your G into joules so that you can use this properly. The R that you want is the 8.31 joules per mole Kelvin. The temperature is 298 Kelvin. And ln K, a number that I don't know yet. And then I can just continue solving. When I do my math then, ln K would be negative 22.45. So I could undo this and I could say that K is equal to e to the minus 22.45. You could solve that out in your calculator and find that it's a very small number, right? Because that's a negative exponent. Or you could stop at one of these 2 points. It's not necessary to go down to a complete number. You could stop at log K equals a number or at K equals a number. And so now we have this way to go back and forth between equilibrium constants and delta Gs. And that's really important to us going forward, because now we're going to turn over and think less about what the number for K is, and we can calculate it, right? I can go look up delta Gs from a table and use delta Gs to get Ks. Once I have Ks, though, I can do all sorts of powerful things because I can actually figure out concentrations. Now that I know this K, I could look at any set of concentrations and I could say, I expect this much silver ion. I expect this much chloride ion. And that's going to be a big project that we spend quite a bit of time on in class going forward.